on the chat box. Okay, for the last class, we learned about the what we call a deflector. All right. So in the deflector, we have two parts: the stationary deflector and moving deflector. For the equation of deflector, it is simply the summation of force, okay, equal to mass flow rate bracket velocity 2 minus velocity 1, okay, or we call as a velocity final minus
Kita tak
initial.
nampak skrin.
Okay, memang belum start lagi.
Oh ya ke?
Because that is just a recap. Okay, remember I explained to you the deflector. We have two components. Okay, moving deflector like this, and the series of deflector in the turbine blade. Okay, in the turbine blade we have the impulse and reaction turbine. Remember that the impulse using the velocity 100%, while the reaction turbine use the pressure and velocity at the same time. Okay, then I talk about the momentum equation applied to this moving deflector. This is a single deflector. Okay, so remember that the force, we have two components, which are X component and Y component. Okay, so from here I explain to you about a series of deflector we call as a cascade of wing. Okay, you can see we have so many deflector. So this deflector move from the left to the right. Okay, we have the fixed jet from the nozzle inlet, and then we have the time average position for the exiting jet. Okay, from these deflectors, we come up with the triangle vector at the inlet and the outlet. Okay, so this is how to get the power output from the moving deflector, which is W dot. Okay, this is the work dot represent the power. Okay, because work divided with time is the power. This W dot is simply the power. Okay, let me write this. This is actually, okay, W dot is the power. Okay, W alone is the work. Okay, we have the work, or simply the energy. Okay, the work have the same unit as energy, which is joule. Okay, so how to get the power output from the series of turbine? N represent the number of blade. R is the reaction force that have holding the blade, and VB is the velocity of the blade. Okay, so now we move on the propeller. So what's the function of propeller? Of course, to propel the fluid, right? It is the gas or water or oil. To remove the oil from the factory, we use the propeller. So how do we categorize, how do we solve using the fluid mechanic for this propeller? Okay, thus we need to form the stream tube. Okay, can you see this is like a tube, stream tube. What is a stream tube? Stream tube is the connection of the streaming. Okay, this is actually the streaming of the particle moving at the same path, trajectory, continuously. Okay, from the inlet to the outlet. Okay, now please imagine we have the flow like the stream tube across the propeller. Okay, so we have the inlet, and of course we have the outlet. At the middle of this, let's say we consider as area 3 and area 4, close to the propeller. Okay, so inlet area we name as area number 1, and the outlet area we name as outlet number 2. Of course, at the middle we say as 3 and 4. This is a 3D view. To ease your understanding, let's take a look of the 2D view. Alright, so this is the 2D view of the stream tube. Alright, so for this case, we have the inlet and the outlet, point number 1 and point number 2. Close to the propeller, very close to the propeller, we have area 3 and area 4. Okay, and we have the velocity v1 and we have the velocity outlet v2. Okay, so from this case, how it works, the momentum equation in the control volume between section 1 and 2 give, okay, remember that the momentum equation simply have summation of force is equal to mass flow rate multiplied with V2 minus V1. Okay, just remember this is the momentum equation. It's very simple. Okay, since the area 1, area 2 are not known, alright, we don't know about area 1 and area 2 size. Another control volume is drawn close to the propeller. That is why we need, okay, we have 2 unknown. Definitely we need something that we know already, okay, in order to solve. Okay, for example, like simultaneous equation, if you have 2 unknown, you need to have 2 knowns. Alright, you need to know 2 things in order to get 2 things. Okay, so that is why you have 3 and 4, the area. So let's say we consider the velocity. Okay, what do you think of the area 3 and area 4? Do we have any clue what's the size of this area? Anyone? What do you think, area 3 and area 4?
Area 3 is larger than area 4.
Okay, correct. So what happened when this control volume is very close to each other? What do you think, the area 3 and area 4? Is it approximately equal to each other? Okay, when the control volume is very close. Can you see? The control volume is drawn close to the propeller. Okay, that is why we assume the area 3 almost equal to area 4. Okay, now you understand, yeah? So because of this, apply the continuity equation Q equal to AV. Okay, we know that Q3 and Q4, okay, is the same. Okay, based on the conservation of continuity. So area 3 V3 equal to area 4 V4. Area is the same. Can we cancel the area and area 4? Thus, we get velocity 3 is actually the same with velocity 4. Very simple. Okay. So, neglecting the viscous effect. So, what is the viscous effect? The viscous effect is like this. It is causing the friction. So, when we neglect the viscous effect, that means the velocity flow is uniform. Okay, uniform flow from the top to the bottom, the same constant velocity. Okay, this is like uniform. This is what we call as negligible viscosity. And realizing that pressure 1 and pressure 2 is exposed to the atmosphere, that is why pressure at point 1 is equal to pressure atm. Then we can consider, okay, as the gauge pressure is 0. Pressure at point 2 is exposed to atmospheric pressure, so P atm equal to 0. Okay. Now considering the Bernoulli equation at point 1, 2, 3. Can you see 1, 2, 3? The Bernoulli equation. So what's the Bernoulli equation? We start with the pressure first. Okay, pressure 1 gamma plus velocity 1 squared over 2g. Okay. Wait, yeah. Okay. And then we have the Z1 equal to, this is 1, this is 3. P3 over gamma plus V3 squared over 2g plus Z3. This is the Bernoulli equation. Okay, since at point 1 and 3, you can see 1 and 3 have the same height, thus we can cancel out.
Excuse me, doctor.
Yes.
Can you explain the viscous effect once more?
Okay, the viscous effect is actually causing the friction between the wall. Okay, without the viscous effect, okay, this is viscous effect. This is like a tube. Okay, this is tube. The flow without or neglect the viscous effect, the velocity is uniform. Uniform flow. Okay, this is versus, okay, viscous effect. What do you think when we have viscous effect? Due to this viscous at the wall layer, we have the velocity profile like this. Okay, Iftikhar Rahman, do you understand? The viscous is actually cause the wall to slow down. The velocity near the wall to slow down. Okay? Without the viscous, that means the velocity have no resistance. It is the same for the entire section. Okay, so because of this, we know that Z1 is equal to Z3. We can cancel out Z3 and Z1 and rearrange the equation. Okay, all these terms go to the other side. So we're gonna have, okay, sorry, not this term. Okay, this term move to the other side. So V1 squared minus V3 squared over 2G plus P1 minus P3 over, okay, over gamma. Okay, equal to 0. So this is just a arrangement. And then again, considering the Bernoulli equation from point 4 to point 2. Okay, just now we did at point 1 to 3, and now we are going to do at 4 to 2. The same thing happened again. The pressure at point 4 over gamma plus velocity at point 4 squared over 2g plus z4 equal to P2 over gamma plus V squared 2 over 2G plus Z2. Okay, rearrange the equation. This part move to the, sorry, okay, not this part, sorry, okay. Okay, arrange this part, move to the left. Okay, so P, so start with velocity first. Velocity 4 squared minus velocity 2 squared over 2g plus P4 minus P2 over gamma equal to 0. Let's say this is equation 1. And let's say this is equation 2. Okay. So solving equation 1 and 2 simultaneously. Okay, from this one you solve and combining that the pressure 1 and pressure 2 is actually P atm. Okay, this part is actually, sorry. Okay, this part is actually P atm and this part also P atm. Okay, you can solve simultaneously and finally, okay, you will have this equation which is V3 equal to half V2 plus V1. Okay, this is the combining equation 1 and 2. Okay, you can do mathematically on your own, and finally and conclusionally you will find this. So now we know that in order to get the velocity at point 3, it is the average velocity at 1 plus 2. Okay, it is the average velocity at inlet and outlet in order to get velocity at 3. Okay, so the input power needed to produce this effect is found by applying the energy equation. Okay, now I need to extract. How do I extract the fluid energy from the propeller? So I need to apply the energy equation. Do you still remember how to apply the energy equation? Which is the same like Bernoulli, P1. Now I apply at point 1 and point 2, yeah. P1 over gamma plus V1 squared over 2G plus Z1 plus, this is the work input. Remember the work input, or we call as a work input from the fluid. If we have the pump, we change this F to be the pump. If we have the fluid as the input, we change the pump to be the fluid. Okay, this is just the input power. mg. Remember I explained to you the last time about this input power. Okay, equal to P2 over gamma plus V squared 2 over 2G plus Z2 plus, do we have the turbine? No, right? Okay, and then we consider the heat loss. Okay, for this case, we don't consider any heat loss. Okay, because remember that because of the viscous effect, there is no loss. Okay, so we cancel out this 0. Okay, Z1 and Z2 the same height, we cancel. It is not 0, we cancel only. Okay, and pressure 1 and pressure 2 the same, atmospheric pressure. Okay, we can cancel out. So what do we have here? Definitely we have arrangement. Okay, W dot fluid over mg equal to this one move to the other side. Okay, so V squared 2 minus V1 squared over 2G. Okay, we notice that we have the gravity and gravity. And here the mass flow rate we move to the other side. And finally, we will have the W of fluid. This is energy from the fluid. Okay, equal to V squared 2 minus V squared 2 minus V1 squared over 2 multiply with mass flow rate. Okay. So from this part, we notice that V2 minus V1. Okay, can we do the factorization? For example, A squared minus B squared. When we do factorization, we can make it like expansion A minus B, A plus B. I assume that every one of you know, yeah. Okay, can Amira Hidayah okay. So we know that this is the concept of factorization. A squared minus b squared is a minus b, a plus b. So I want to expand this. V2 minus V1. So from here, I can expand W dot fluid equal to V2 minus V1, V2 plus V1 over 2 multiply with mass flow rate. Okay, and then you notice that V2 plus V1 over 2 is actually equal to V3. So I want to replace this term with V3. Okay, so finally we can say W flow rate equal to V2 minus V1 M dot V3. Okay, so this is the simplification. Okay, this is the moving. Alright, in order to get, remember that this is the fluid energy extracted, this is the input, alright, and this is the output. Because of the energy coming from the fluid, it will cause the deflector to move. That is why this is the power output from the propeller, which is force multiplied with velocity 1. Okay. Remember that the force, the momentum is mass flow rate multiplied with V2 minus V1. Okay, so in order to get the theoretical propeller efficiency, okay, what's the formula of efficiency? Okay, work output over work rate input. Okay, remember efficiency is output over input. So what is the output? Output is the propeller or the fluid? Which one is the output? Which one caused the moving? Anyone? Which one is the input? Please let me know your opinion. Can you see? You already have the answer. The work output, okay, is actually, okay, this is the propeller. Okay, this propeller, the input. Okay, this is the fluid. The fluid will cause, okay, the propeller to move. Because of this, the heating of fluid, the propeller start to move. That is why this is the work propeller. Okay, so this is the work of fluid. Okay, so this is the input, and this is the output, the effect. So from here, work output is the work from the propeller that cause moving, divide with work of the input, which is the energy extracted from the fluid. Okay, so what's the formula of W propeller? W propeller is M mass flow rate V2 minus V1 multiplied with V1 over work rate of the fluid, which is this one, which is V2 minus V1 mass flow rate V3. So now we can cancel out the same term. This cancel, this cancel, this cancel, this cancel. And finally, we have efficiency, theoretical propeller efficiency is actually V1 divided with V3. Can you see this is V3 and this is V1, this is V3. Okay, so far you guys understand how it works?
Yes, sir.
Yes, Doctor, it's clear.
Okay, nice. Let's move forward. Okay, now finish about the propeller. Okay, and then we go about the dimensional analysis. DA. DA is very important when you conduct the experiment. Okay, so what is a dimensional analysis? Dimensional analysis is used to keep the required experiment study to a minimum. Okay, can any one of you explain what does it mean of this sentence? And also give example. Amma, would like to try? Amira? Aina? What the definition? Dimensional analysis. What do you understand? Okay. So, for example, if you would like to conduct a research study, okay, to investigate the input over the output. For example, uh, this parameter, this parachute, yeah. Okay, this parachute. Okay, we have the parachute. Okay, so you want to investigate how long does it take to arrive at the ground. Okay. Okay, so what do you investigate? Normally, maybe you investigate the size, the volume of the balloon, maybe the weight, and then maybe the air resistance. Okay, the air resistance. Some more, maybe the buoyancy force, and then maybe the flow of air circulation, the flow of air from which direction.
Different
So,
air, Doctor.
Different air.
Nitrogen.
Yes, different, maybe nitrogen.
Yes.
And you see, you have so many variables that affect the parachute to fall down, right? So, this is the function, dimensional analysis, that to minimize your experiment. Okay, if you conduct experiment, maybe you will conduct one by one. For example, you conduct different nitrogen, and then you try to use helium. You use different kind of material, fluid inside the balloon. Secondly, you try to change the size, the volume of the balloon. Maybe you have a different weight. You have to conduct one by one. Okay, so it will take a year. Maybe it will take 50 years to complete your experiment. So it is a waste of the time, because your result you cannot apply to other application. So maybe your result can apply to single or only a specific part. But with the help of dimensional analysis, the first, it can reduce the number of experiments. You don't have to carry out a lots of variable. Secondly, you can apply your result can be applied to general use. Okay, so let's recap on the dimensional homogeneity. Okay, in order to apply the dimensional analysis, you need to know the dimensional homogeneity. So what is the dimensional homogeneity? Okay, all the term in the equation should be the same dimension. Okay, the dimension is m, mass, the length L, the time T. Okay, all that we call as a dimension. So what it means here, let me explain to you. Okay, so for example, we have let's take a look of this dimension, the first part. Okay, the first term. This is the first term. Okay, the first term, velocity 1 squared. Okay, so velocity 1 squared, which is what's the unit of velocity? That is meter per second negative 1. When it is squared, it is meter squared second negative 2. Divide with 2g. Divide with 2g. So what is the formula? What's the unit of gravity? It is the same with acceleration. Okay, so meter second negative 2. So here meter second negative 2. Can we try to cancel? Second negative 2, second negative 2, meter. So what we have here is actually meter per 2, or simply meter is the length. That is why the dimension here is length. Okay, let's take a look of the second term, which is P over gamma. Okay, so what's the formula of pressure? Force over area. So what's the unit of pressure, everyone? The unit of pressure.
Newton per meter square.
Yes, perfect. Newton per meter square. Okay, and then divide with the gamma, specific weight. So what's the unit of specific weight?
Kilogram.
That is the mass.
Kg per meter cube.
Kg per
Meter cube.
that is the density.
Newton per meter cube.
What? Newton?
Per meter cube.
Not meter cube. It is actually Newton per meter only.
Yes.
Okay. So now try to cancel out Newton, meter, and then you will find that your M is actually equal to M. So M is the dimension of L. Can you see the same dimension, L and L? Okay, can you see the third term? The third term is Z. Z is a meter. Okay, so the dimension of L. Can you notice that the first, second, and third all the same dimension? That is why we call it as a dimensional homogeneity. Okay, so far you guys understand what means by dimensional homogeneity? Okay, clear so far. So, proceed with the experiment that require to be, we need to minimize the number of experiment. So, now we introduce you with the Similitude Study, which is a study of predicting the prototype condition from the model observation. Okay, let me tell you in a clear manner, all right? For the engineering company, if they want to develop the prototype, something in the real life, they need to model first, okay? Sometimes they need to model using the computer programming. They're using the MATLAB, they're using the simulation software, they use the theoretical calculation in order to predict from the model to the prototype, okay? So for example, if they want to create the aircraft, so for the current technology, definitely they will create the 3D model and they will do the simulation. and do the calculation and theory to make sure the aircraft can fly. Okay, without having the model, then definitely it will have the highest risk for the engineering company, especially when they want to develop $1 million of prototype. Okay, so that is why they need to create the model. So how they investigate? For example, this is the car. Okay, so how they investigate? This is the model. And how they investigate the real car. The real car in terms of performance. How they investigate the performance of this car. Okay, maybe this is lorry. How they investigate? They use the similitude study. Okay, similitude. Okay, similitude. Okay, that means the model will behave the same like the prototype. Okay, so they investigate from the model, so it will be happen in the prototype. So how they use the dimensionless parameter to obtain the dimensional analysis. Okay, so this is we call the study, we call a similitude. Okay, the method we call as dimensional analysis. This is the method. How they conduct using the dimensional analysis. Remember that when they use the dimensional analysis, first they must make sure the equation is homogeneous. Okay, have the same dimension. So there are two approaches for the dimensional analysis. The first, Buckingham Pi theorem. It sounds nice to hear. And for this course, we going to discover the first part only, the Buckingham Pi theorem. Okay, it is only step because the Buckingham Pi theorem is the step-by-step approach in order to get the solution for the dimensional analysis. Okay, for this part, this is quite tricky. You need to extract the dimensionless parameter from differential equation and boundary condition. Okay, this is just the expert level because this is required the experiment, the simulation, all this. Okay, so this is the example. As I explained to you, how do we minimize the number of experiment? For example, this is the pipe, the cross section of the pipe, and then we have the slider plate. So the function of this slider plate to reduce the velocity of the flow from the inlet to the outlet. Okay, so you look at here, the pressure drop across the slider valve. Okay, the pressure drop significantly. From here you can see the indicator P1 to P2, the pressure drop, yeah, because of this slider. So from here we can assume that the pressure drop, okay, depends on the pipe mean velocity, the fluid density, the fluid viscosity, diameter, and the gap height. So from this, how you investigate the pressure drop? There are so many parameters. For this case, it is the velocity itself, the initial velocity, the density of the fluid, the viscosity, the diameter of this, and the gap. So, and then you form the relationship, okay, which is the pressure drop as the independent variable equal to the function of velocity, the density, the viscosity, diameter, and height. Okay, all these variables, 5 variables, affect the pressure drop. So how do you conduct the experiment? So conventionally, you will conduct one by one. For example, you will conduct velocity first. You change the velocity, all these fixed. And then you fix the velocity, you change the variable of density. You vary the density, and then you vary the viscosity until the DNH. So can you see how many of numbers of experiment have you done? It's so many. Okay, you have this, and then for example, this parameter maybe you conduct from 1, 2, 3 until maybe 100 meter per second. And then viscosity, you conduct density 1, density 2, until thousands of density. You don't have any limit, right? So that is why I explained to you. The number of experiments so many. Okay, when you don't have the dimensional analysis. Okay, this is like the example. You conduct one by one. This is the pressure drop, this is velocity. And then you change the diameter. And then the pressure drop, this is velocity. You change the height. This is the conventional way, and it is very huge number of experiments. Okay, so by using the dimensional analysis, you can perform only single experiment. How to do that? Okay, the equation could be written in terms of dimensionless parameter. Okay, instead of delta P equal to the functions of velocity, density, viscosity, diameter, and height, you can transform this equation into this. Okay, this is what we call as dimensionless analysis. Because this, you can see the first term, the left hand side is unitless. The right hand side also unitless, no unit. It is homogeneity. Okay, so from this equation, you will find this is like a y axis, and this is the x axis, and this is your variable. Okay, you change only this variable, you only have to conduct this single experiment. You don't have to conduct a series of experiments. Okay, because of this experiment, they use the ratio, okay, to discover the correlation between the independent variable to the dependent variable. Okay, this is independent. Okay, this is dependent. Okay. So later on, I will explain to you the next class. I will explain to you more on the dimensional analysis. Okay. So this is the final part. This is just a review. Okay. The dimensional analysis a review. All quantity have a combination of dimensions of length, time, and mass. Okay, we call as an MLT system. MLT. Mass, length, and time. Okay, based on the Newton's second law, which is F equal to MA. In terms of dimension, we know that mass. So what's the unit of mass? Kilogram. So what the unit of acceleration? Meter per second squared. Okay, and then we convert the kilogram in terms of system. Kilogram is the mass, so mass. The meter is length. The second is time. So this is in terms of dimension. So all this term is actually can be found in table 6.1. Okay, when we want to locate the length, the symbol L, the dimension is capital L. When we need to find the density, it is meter per length. For example, density. What's the formula of density? Mass over volume. So the unit of mass is kilogram. The unit of volume is meter cubic. So kilogram is the mass. In the dimension, it is capital M. For the meter cube, it is length multiply with length multiply with length 3 times. That is why you can see the density the same with M per L cube. Okay, so far you guys understand the review of dimensional analysis?
A little bit confused, but yeah.
Okay, which part do you confuse?
The last part that you mentioned.
The last?
The last part you mentioned. That you said the dimension.
Okay, this is the dimension. Please remember the dimension is in the unit of capital, all the capital letter. Okay, the dimension for the length is capital L. Okay, for the time it is capital T. For the mass is the capital M. That's it. You need to remember this. Can you? For the dimension MLT. Dimension, you need to know MLT system. That's it. Mass, length, and time. Amal? For example, pressure. So what's the pressure? Force per area. So what's the unit of force? Anyone? So what's the unit of force?
Newton.
Newton.
Newton?
Newton
I
بمتر
think
Newton only. Force.
متر
Newton like meter.
Okay.
Meter square.
Newton per meter square.
Square. Yeah.
Okay. So Newton, the force. Okay. So the force equal to mass multiplied with acceleration. Let me. Okay. Can you see this one? The force is ml over t. Okay. So ml over t squared divide with m squared. M is the meter, right? Meter is the dimension of what? Meter is the dimension of m, l, or t?
L.
L squared. L divide with L. So you will find that m over L t squared. This is the dimension for pressure. Can you see this one? Where is my pressure? This is my pressure. Can you see? It is the same. Okay. Now you got it? So
yes, doctor. Thank you.
this is velocity. So what's the velocity? Let's say this is velocity. Velocity, the unit of velocity is length. The formula is length over
Meter.
time.
Time.
Okay. So meter per second. So meter, the dimension of meter is what? MLT system. MLT system. The dimension of meter is what? MLT system. This is mass. This is length. This is time.
Yes.
For the meter, which one?
L.
L. So what's the for the S? MLT.
It's time.
Can you see the dimension of velocity is L over T. Okay. So everyone, you guys understand about the dimension? Okay, I think it is pretty easy because you need to list out the formula first. For example, velocity, which is meter per second. From meter, check from MLT. Meter represent what? The length. Okay, length. The second represent the time, L over T. So now you got L over T. Okay. Do you have any questions so far? Area. Area, you can see area is length multiply with length, or meter squared. So meter, what's the unit of what's the dimension of meter? The length, L squared. Can you see here? We have the meter, we have the area. Okay, so far you guys managed to catch up about the dimension.
Okay, Doctor.
Okay kan, it's not so difficult because it is just checking the MLT system je. Okay, I need you to remember MLT je, not so difficult. MLT. Okay, I think that's all for today. Okay, thank you very much for your time. It is only 1 hour and now we covered about the dimensional analysis. We cover the propeller in theory as well as the deflector. Okay, I already posted the tutorial question on this chapter. Please look at it in order to understand by working on the example.
Okay.
Sir, can you please show the attendance? Thank you, sir.